Welcome back, guys. I can already see that you guys have joined us, which is very nice. And if you have just joined us, we are doing the prelim paper from last year, hey Phil?
Well, it's the final paper.
The
Actually,
final
this is
paper
the
from
big
last
one.
year. Okay, so this is the big one. Get those papers out, guys. Ask people for them. Download them. You know that there's many sites that you can download them for free. Do as many as you can because they really do help you.
Absolutely.
Over to you, Phil.
Thank you so much. Okay, well, again, we're going to jump straight back into these. Let's get these multiple choice questions out of the way. Let's see if we can move it a little bit faster. I really want to get into the long questions, which is where people really struggle. Okay, now, please, guys, one of these graphs, please don't be scared of it. Okay, it's going to be in your exam, but the nice thing is it's very predictable. Okay, let me explain what we've got in front of us. The Maxwell-Boltzmann curve over here, these energy diagrams. Okay, now they are fairly new to the syllabus. Now, all they tell us is how much of our substance has got the required amount of energy to react. Okay, so let's just pay attention to our axes here. The number of particles and the kinetic energy. So that means that the higher the peak is, the more particles we've got, and the further to the right we are, the more kinetic energy they've got. Okay, well, let's take a look at option A, B, C, and D when we consider which one of these curves represents a reaction with the highest rate. Okay, now inside our description, it tells me that there's this line. This line is a dividing line. So let's just actually make it nice and loud and proud. Okay, so this dividing line, let's just make sure that it lines up perfectly. There we go. That line is the minimum energy required to react. That is the activation energy. Now, a molecule must have more than that amount of energy to collide to make an effective collision. Okay, now what I see if I analyze these curves, if I analyze curve A, look to see that there's a lot of particles which have too little energy. As I go to option B, what happens is my particles start to gain more energy. I'll find that they're more distributed and more of them lie to the right of the graph. Option C, I find that now there's a significant amount of particles which have got enough. But now here is where my interest lies. Option D is the one. Now I'll tell you why. Option D has got a whole bunch of its particles all the way to the right-hand side of that line. That means that they've got more than the required amount of energy. So if I color in the area there, most of curve D actually tells me that I've got enough energy. So this one's actually quite a quick one. We know that option D is our correct one. So option C, B, and A, let's just cross those out. Okay, option D was the easy answer here because it lies furthest to the right, and that means more molecules have enough energy. Okay. Now this one seems to come up almost every year. A certain chemical reaction is represented by the potential energy diagram below. Now I just want you to pay attention to some of the important pieces of information here. I start out with my initial energy. That's the energy of my reactants. I finish up with the energy of my product. So let's just label that. So I start out with my reactants. That's where I begin. Okay, and then I end up with my products. My products lie all the way down here. Now, my reactants and my products have got certain amount of energy inside the bonds of the chemicals. That is something that you cannot change. You cannot change the bond energy of your reactants and the bond energy of your products. That is something that is a result of different chemicals bonded. That cannot change. That's a little bit of a hint. Now it asks me, which one of the following quantities will change when a catalyst is added? Now, I've already told you that the energy of my reactants and the energy of my products is decided by the chemicals. It's not decided by conditions or anything else. So E1 is my reactant's energy, E2 is my product's energy. Now, let's just take a look at something else. My EA, my activation energy. Activation energy is the energy that's required in the collision between these two reacting particles. So activation energy is something which I can actually influence. I can make things a little bit easier by introducing a catalyst. What I'll find is that I can actually make a slightly different line. I could make a new curve which does that. Notice how it starts and ends in exactly the same place. If I change that curve by adding in a new catalyst, I've lowered the activation energy. So I need you to know that that is what a catalyst does. It lowers the barrier. It makes it easier for reactions to happen. So I find that option C is probably the correct one. Let's just get rid of option D to make sure. Okay. Now I remember I told you that option E, 1 and 2, can't be changed. So the difference between them can't be changed either. Delta H is fixed for a particular type of reaction. Doesn't matter what catalyst you put inside it. So I know that option D is not the correct one. We're getting there, Matrix? So hold on tight. Let's keep on going with this. Okay, option 2.7. So let's get into this question. When a metallic atom, okay, let's just take a look at what a metal really was. A metallic atom. Those are the atoms which I find on the left-hand side of the periodic table. It becomes an ion. Okay, well, what's so special about metals is because metals like to make positive ions. So let's read through our options. Okay, how do I make a positive ion? Well, how do I go from having M, which is my metal atom, to being M+? The only way to become positive is by losing electrons. You cannot change the charge on something by adding or losing protons because those are nuclear reactions. Don't even go there. The only thing which you can easily move onto or off your atoms themselves are electrons. Okay, so let's take a look. To go from metal to metal positive ion, what I've got to do is lose an electron to leave behind the positive. So let's just take a look at our options here. So now I think option A might be it. So loses electrons and is oxidized. I think that's right. Now the thing which leads me to think that it's right is because loses electrons, yes, this would make a positive ion. Oxidation is the loss of electrons. Let's just take a look at the other options and see what goes on. Okay, well option B also says it loses electrons, but the loss of electrons can't be reduction. So that's wrong. What happens if it gains electrons? That's wrong. We know that its gain of electrons would make it negative. Okay? And the gain of electron can't even be oxidation. It gains electrons, can't even be. And is reduced, well, reduced kind of agrees with gains electrons, but the only one which is a clear choice over here is option A. Option A has got everything that I need. Okay. Question 2.8. Which one of the following substances cannot, please, guys, okay, cannot, again, please don't be a rebel. They're asking you to find one that can't be used as a fertilizer. Okay, now, this is a little bit of revision on some of the chemical systems that we're talking about. Chemical systems, in terms of fertilizers, we're talking about types of substances which can be dissolved into the soil so that plants can use them. So when I talk about a fertilizer is something which must be able to be dissolved into the soil. Okay, let's take a look at our options. We've got nitrogen gas. Now remember that N2 gas is non-polar. Non-polar things can't dissolve in water. So I think I've got my options straight away. Nitrogen gas cannot be used straight away as a fertilizer. That's why we need things like nitrogen-fixing bacteria. That's why we need the Haber process. These all make nitrogen soluble. Nitrogen gas is not suitable as a fertilizer. And that's why plants need other things to get nitrogen for them. Either bacteria on their roots or in the soil, or lightning, or the Haber process, or artificial fertilizers. Nitrogen gas is a terrible fertilizer. It's all around you and you're busy breathing it in right now, but you cannot use that nitrogen. Okay, guano. Now this is a bit of a weird word. Okay, guano refers to bat droppings. Now guano used to be a very, very important source of fertilizer, especially about 100 years ago before they developed the Haber process in great quantities. The guano, or bat droppings, is very, very rich in nitrogen and potassium. Okay, so guano definitely can be used as a fertilizer. It can dissolve into the soil and feed plants. Okay, bone meal. Okay, bone meal is definitely a fertilizer. Now, let me just remind you that bone meal is a very rich source for the plants of phosphorus because bones are full of phosphates. Now, bone meal slowly dissolves into the soil. It gives it phosphates, and the calcium in the bones actually neutralizes soil acidity and controls it. So bone meal is actually a pretty good fertilizer to add into a soil. Ammonium sulfate, let's just take a look. Now, ammonium sulfate has got that NH4. There we go. There are two of them. Here's your formula. You should know this already. Ammonium sulfate has got lots of nitrogen on it. Now that means that this is definitely a fertilizer. Ammonium sulfate, just as a background, ammonium sulfate is actually a very good way to lower the pH of soil. So some plants, especially pine trees, like to have acidic soils. So I'll use something like ammonium sulfate to increase the acidity. Okay, we're into the last two questions. Let's see what 2.9 and 2.10 hold in store for us. I've got to consider two half reactions below that occur inside a battery. Now I've got to be very, very careful because neither one of these actually fits on my redox table. Okay, so now what I've got to do is I've got to start using my brains here and I've got to see what's going on in each case. It's all about the electrons, and that's all redox chemistry actually is. If you look to see where the electrons are, that'll tell you a lot. Now, in my first reaction, I see electrons on the right. In the second one, I see them on the left. Now, that tells me a huge amount about these two reactions. If I see them written the way that they are, what I can tell immediately is that the top one is that there are a loss of electrons, or that there is a loss of electrons. That makes this into an oxidation half reaction. The second one, I see electrons going in on the left-hand side. That means that I've definitely got electrons joining on with something that is reduction, that is a gain of electrons. Now, I suspect that that might have already answered half of the questions. Let's take a look. Which one of the following statements is correct? So I'm looking for the one which is correct. Let's consider this. Now, it tells me that Ag solid is reduced. Okay, well, let's look to see where Ag solid actually is. I see Ag solid over there. Is it possible that it's reduced if it's a product? It's coming out. That can't happen. Let me just repeat that again. Ag solid is reduced. Now, this is how tricky your examiners are. I see that the silver reaction has got reduction. And I think, oh, I've got the right answer, but that is absolutely wrong. I cannot reduce a product. Okay? ZNS is the anode. Well, if I've got zinc as a solid, it does participate in oxidation. So that actually looks right. Oxidation happens at the anode. That looks to be a good idea. Let's take a look. Silver oxide solid, there it is the negative electrode. That one's quite tricky. Now, what I've got to do is I've got to realize that this reaction is using electrons. It requires electrons to happen. So what starts to happen is that the electrons are being gobbled up. Now, if I gobble up all of my electrons, what I'm going to be left with is a positive charge. If the electrons are going in and they're being taken up by something, I'm going to leave a positive charge. So C is incorrect and B looks to be still the correct one. Then the last one, electrons are transferred from Ag solid to zinc solid. Well, I'm still not entirely sure about this because this looks like electrons need to go to the silver electrode and away from zinc. I can see that a zinc is giving off electrons. There they are. Zinc is giving them away. So this last statement can't be correct. Now, what about our last one? Let's get there. Okay, now this last one is a little bit of a tricky one, all the way back from grade 11. Okay, the oxidation number, this one's tricky, of copper in the compound of CuSO4. Now, let me just show you how to work out oxidation number. So CuSO4, I'm not sure what copper is because copper is a transition metal. Okay, what I've got to do is I've got to make a small sum. I say copper because it's unknown. I'm going to treat it just like X in maths. Plus, now I know that sulfate Sulfate itself has got a charge, which I know. And if you can't remember it, just look on your redox table. Sulfate has got a -2 oxidation state. Okay, so I know that sulfate is -2. When I add these two ions together, I must add up to 0 because copper sulfate is a neutral compound. So copper plus -2 equals 0. Let's solve this just like a maths equation. What I'll find is that copper minus 2 equals 0. And that means that copper is equal to +2. But I think it's time for a short ad break before we get into those long questions. What do you think,
Okay,
Kat?
let's do that, fool.
Okay.
So guys, we're gonna go for a really short ad break. Someone said on the page, Munaka says, I don't think we need an ad break. I know, I also don't think we need an ad break. But just for your refreshment, please may we take one. See you right after the break.